Today I'm going to talk about a non-Euclidean vector product which we use in neural network design. I am Enis Çetin. I'm with the University of Illinois at Chicago. I'm on leave from Bilkent University, and the other authors are with the Middle East Technical University. We have visa problems. I couldn't come to Canada because of this visa issue. So I'm presenting my paper via YouTube, or one of our students from the University of Illinois at Chicago will present on our behalf. Okay, here is the outline of my talk. I'm going to define a multiplication free operator which we use in the new non-Euclidean vector product, and then I'll describe how we use this non-Euclidean vector product to develop additive neural networks. I'll cover the properties of additive neural networks. I'll present experimental results on MNIST and CFAR dataset, and finally I have the conclusions. So our main motivation at this point is to develop energy efficient networks. As you know, convolutional neural networks are computationally expensive, and you have to perform many multiplications, and multiplications consume energy in a cell phone or in a mobile device. So we have this operator which replaces the multiplication operation with an additive operator, and we use it to define a vector product which is related with the L1 norm, and as a result the neural networks that we get are energy efficient neural networks. Okay, so here is the definition of the operator. So let's assume that x and y are two real numbers. X plus y is defined as sine of x times y times absolute value of x plus absolute value of y. So we keep the sign of the multiplication, but we add the magnitudes of the two real numbers x and y. So if I have minus 3 plus 5, I would get minus 8. If I had minus 3 plus minus 5, I would get plus 8 instead of plus 15. So I don't perform any multiplications, and I compute the sign using the XOR operation. Now this operator can be also implemented in this way: sine of x times y plus sine of y times x. And we use this equation to design the neural networks using TensorFlow or other readily available software. And essentially the operator does not require any multiplications. And we extend this to a vector product, x plus y. X and y are vectors. It's basically summation over I, xi plus or o plus yi. And it's summation I sine xi times yi, absolute value of xi plus absolute value of yi. The multiplication free operator is related with the L1 norm. So if I have x o plus x, I get 2 times the L1 norm of x. So in a way, the operator induces the L1 norm So, the inner product induces the L2 norm, and this operator, we may say that this new vector product induces the L1 norm. And as I just pointed out, we don't perform any multiplications. Actually, during the implementation, we sum the magnitudes and we use the XOR operators between the operands signs to determine the final sign. And so we have some sort of a correlation here, correlation operation. So this non-Euclidean vector product can be thought of as a special form of correlation operation. Now, one problem with it is that it's not smooth. So I have here the plot of x times y for x and y in between -1 and 1. So I have, in a regular multiplication, you have a smooth surface, but here you have discontinuities, and this discontinuities may lead to some problems during the design of the neural networks. Okay, so this is like a correlation operation. Therefore, I can use it in neural network structures. You have now an typical neural network neuron here. So instead of multiplying weights by the entries of the vector, we perform the O plus operation. Okay, so x1 O plus wk1, x2 O plus wk2, xm O plus wkm goes into the activation function. So this is an additive neural network. This is an additive neural network because we don't perform any multiplications here. And the O plus carries the correlation information. So we can use it in any type of neural network, including the convolutional neural networks. So we just replace the regular neuron with our additive neuron. And so obviously it doesn't require any vector multiplications. In practice, we observe that we need a scaling factor. We actually use the ReLU activation function in this neural network, and we observe that we have to change the slope of the ReLU. On the positive side, so in each neuron we essentially perform a single multiplication. We have the scaling function in each neuron. Okay, a sub I sub L is the scaling factor here, and we perform a single multiplication in each neuron. That is the slope of the ReLU rectified linear unit function. So, and we learn these weights during batch normalization. Okay, so how do we train the AddNET? We use standard backpropagation algorithm during training, and it requires derivatives. And we can compute the derivatives of this O plus operator. So, for example, I have here the partial derivative of W plus X with respect to W, the weight, and it is equal to sine X plus, the signum function of X plus 2 times X delta W. And this is the dual derivative. Delta is the Dirac delta function, and we cannot compute this, but this is 0 except W is equal to 0, and Since w is equal to 0 or x or n or x is equal to 0 cannot happen in practice, we can omit the Dirac delta component from the derivative to obtain the approximate derivatives. The probability of w equal to 0 or x is equal to 0 is equal to 0, or they are sets of measure 0, so we can ignore them. And we use these sign-based derivatives in backpropagation algorithm. We also use the stochastic sign operators used in binary connect. We need, of course, vector and matrix operations, and we can easily generalize the derivatives. However, the convergence is much slower than regular neural networks because of this sign operation. And there is also the adaptive filters, sign LMS adaptive filters. So the training is essentially similar to the sign LMS type algorithm. So let me present some experimental results. So first, let's take a look at the MNIST data set. And we have this convolutional neural network, and it consists of, we use this structure. It has two convolutional layers and a fully connected layer, and finally a softmax layer. So in the convolutional layers, actually that's the computationally demanding part, we have the AddNET, and in fully connected layer and softmax layers, we use just ordinary multiplication operations. And if you use the ordinary regular neurons, you get a recognition rate of 99.2%. In AddNET, we get 99% recognition accuracy with L1 normalization. The scaling factor, which is basically computed as the weight. We have this normalization factor, absolute sum of the weights divided by the filter height, width, and depth. H, W, and D represent the filter height, width, and depth. We also tried various other parameters like standard deviation, etc., but they don't produce as good results as this. This is obviously the best one in terms of computational accuracy, computational cost, and recognition accuracy. And these are the other parameters of the training. A batch size of 64 is used. As I pointed out earlier, the ReLU activation function is used, and the cost function is crossed entropy with softmax, and we have the momentum update rule. Okay, in CFAR10 data set, obviously this is a more demanding data set. So we have a deeper structure. We have more convolutional layers, and finally we have two fully connected layers and a softmax layer. And the other parameters are given here. In this case, when we replace all layers by the multiplication-free operator, our classification accuracy is 85%. When we keep two fully connected layers as regular neurons, and the softmax at the very end as the regular neurons, we get 90.6% 7% recognition accuracy. We use stochastic binarization during training, and we use batch normalization during network training. And I have here a slide describing the stochastic binarization, which is introduced in the binary connect. So it gives us a better convergence, and we thank one of the reviewers suggesting stochastic binarization. Our results reported in the paper are lower, recognition rates are lower than this. With stochastic binarization, we get better recognition results. And these are the other parameters that we have during the training of CFAR10. So in this talk, we introduced additive neural networks, and we constructed additive neural networks using this multiplication-free operator, which is based on, which leads to a non-Euclidean vector product. And that's how we construct our neurons. AddNET is more energy efficient than regular neural networks because of the reduced number of multiplications. And AddNET can be used in mobile applications because they don't consume as much energy as the regular neural networks. And we demonstrated that AddNET can achieve high classification accuracy on MNIST and CFAR10 datasets. So our goal is to introduce AddNET as a trade-off between binary neural networks and regular neural networks. And I uploaded this presentation on YouTube. Thank you very much for listening. If you have any email questions, you can email it to me. Thank you again, and I'm sorry that I couldn't make it because of this visa problem. Actually, Canadian government issued me a visa, but I have to mail my passport to Los Angeles, and I don't have time to do that. Unfortunately, the Canadian consulate in Chicago cannot handle passport or cannot stamp visas on passports. I didn't know about that. I apologize for this. Thank you again.